Here's a 2.3 problems tutorial. I know you can read, so stop and read the paragraphs and the information before you really dig into a problem. Pause and have a think. Rewind as much as you need. Email me questions, of course. All right, before we even get into this, I realize we got to cover something else that they kind of think you know to get into this. We talked about equilibrium expressions before, and we talked about Le Chatelier's principle, and we said that a system at equilibrium will shift left or right, depending on how you stress the system. It will shift to relieve the stress. So if I make up a little fake reaction here, and the double arrow means it's running both left and right equally at this point, then it's at equilibrium. And we said stuff before, like if you give this more product, chemical C, then it will shift left and you'll get more A and B and so forth like that. That's not really our point at the moment, but what we do need for what I'm about to say is an equilibrium system. We need stuff that can flow. We need a reaction that can react both to the right and to the left. And in this case, what I'm talking about right now is stuff that's dissolved in water. You notice the brackets, and brackets means molarity, which is moles per liter of solution. This also works for gases, because gases can also flow and interact and meet various other molecules in any given second. There is a Kp, but we're gonna for pressure, but we're not going to talk about that right now. We're going to talk about Kc for concentration. K is our constant number again. It's going to come up over and over. Actually, there are different variations. It's confusing, frankly. There's capital K, there's little k, and what do they mean here? And we're just going to have to learn to roll with it. The idea of K was used multiple times just in this class, and probably some other ones I'm not even really aware of. This is a capital K, and sometimes we just start skipping the C because, I mean, what else did you mean kind of thing. And then there are some variations on that theme, which essentially are just specialized versions of Kc. There's K for acids, there's K for bases, and so forth, but really it's just more specific versions of K for concentration, because we will be talking about concentration when we talk about those also. So if you have a system that's running just as strongly to the right as it is to the left, then there's something really cool that turns out happens mathematically, and somebody much smarter than I am, I guess, figured this out, and I've never really figured out who or how or even why this really happens. I've had to ascribe it to, well, that's the way God made it or something. I'm sure that's inadequate. But anyway, what we're going to do is introduce a phrase that's going to come up a whole bunch, which is products over reactants to the power of the number in front. Products over reactants to the power of the number in front. I'm going to say it again, products over reactants to the power of the number in front, to where you can just chant this in case you get stuck in the panic on the test, right? So we're going to take the product, and we're going to use the value of the molarity, because brackets means molarity, right? To the power of a number in front in the balanced reaction, over the value of the molarity of the reactant to the power of the number in front, the invisible 1 comes here, times, not plus. I know there's a plus here, but this is multiplied by the molarity value of B to the power of the number in front. And I know that sometimes I make a big point, oh, just because these numbers are the same, that's a coincidence. This is not a coincidence. That is very, very much why this is squared, because of this 2, and this is squared because of that 2, and this is the power of 1 because of the invisible 1 here. So that lets us do something. Once we experimentally determine what K is, and I've never even seen anybody do it, but it's been done, you can figure some stuff out. If you know the value of C that you want to make in your equilibrium, right? If you look up K, because it's just a fact, you just go look it up, then you could figure out and how much you would need of this. Like if you know you want to use this much A, you could figure out, oh yeah, then we would need this much B. If you know C and you know A, you can figure out B. If you know B and A, you can figure out C, etc. So it becomes really, really useful, especially when you're dealing with acids and bases and we're trying to find pH. And one of these is H+. We can solve for H+, and then we could go and use negative log and so forth and get pH. So go read this and you're back. So we have a reaction. Don't forget this part here, which I did. So the reaction includes this part. Here's a reactant and the product. And the rate has been experimentally determined to be this. This is true. We're confident because we did the experiment and we were very careful. and we made a big data table, and we did it 10 times, and this is the rate law, and we're really, really confident. So how does this reaction happen? Does it happen just all at once, or is it a series of steps? Well, someone proposes that there are 3 steps. This one, this one, this one. Maybe pause and give that a read through. And that, they say, step 1 and 2 are fast equilibriums, and step 3 is the slow step, or the rate determining step. Rate determining step, I would learn that phrase. The test makers like that phrase. So we said when the slow step is first, you can just disregard everything, and the rate is the slow step rate law, and that's it, which is true, but the slow step is not first here. It depends on how fast these fast ones are. And by fast, we just mean faster than this one. These 2 are faster than this one. So the fast equilibrium steps are supplying products to the slow step. This is supplying I singles. One of them goes here, one of these 2, and one of them goes here. And the IH2 that's supplied by step 2 goes here. And those are intermediates. They are not in the overall reaction, right? That's going to become key. So for the slow step, or for any elementary step that's not at equilibrium, the rate law is determinable by the simple balanced reaction. So just for this one step, not for the whole thing, just this one step, I can write a rate law just for this one step. So the rate law for step 3 would be rate equals K times the reactants to the power of the number in front. So IH2 to the first power times I single to the first power. Here's where this starts to get tricky. IH2 is not an official overall reactant. It was not supplied by whoever's supplying this, you or me or nature or whatever. It's not coming in from the outside. IH2 is being supplied by step 2. So however well this delivers IH2 governs how fast this arrives. We know it's arriving faster than this one can use it because this is the slow step. So step 2 is making IH2 faster than this one can take it. Step 1 is making I single faster than this one can take it here. It doesn't matter which step you approach, by the way, in our next discussion, pick one. I guess I'm going to do step 2. Step 2 is supplying this. Okay, so in my rate law, there's an IH2, but I don't get to just call it, hey, IH2, because that's not something I control. The reaction controls it. So can I substitute in for something that uses stuff that I know about, that I can control, that I can see? So we said that any equilibrium is governed by this kind of math. So what we're going to do is write out an equilibrium expression for step 1 and step 2. And why are they at equilibrium? Because, say, step 1 is trying to deliver I singles faster than this one can take them. I know one of them went here too, but the I singles that aren't being taken by step 3 are building up. What happens when you build up a product in a system that's able to go left? Well, it goes left. And at some point, fairly quickly, you're going to get an equilibrium. And step 1 is going to set up an equilibrium. That's why we've got the double arrows. And this is going to run left just as hard as it runs right for any given split second until one of these is taken up by one there, but also one of these is taken up by step 3. So let's write out a K expression for our fast equilibriums. Remember, it was K equals products of reactants, both the power of the number in front. So we get K for step 1, K for step 2. Maybe hit pause and give that a think. Why did I do that? Because I want to substitute in for I single. What is I single worth? Well, if I solve this one for I single, I get this. And now I have something I can mathematically substitute in for I single, and that became this. This is our substitute mathematically for I single. If I solve this one for IH2, I get this, and this is my mathematical substitute for IH2. I tried to draw an arrow here, right? That comes in for IH2 and becomes this. Actually, we should include the K2 there. And it just means it's the K from step 2. This is all it means. K1, K from step 1, K from step 2. So this substitution went in here for IH2. This substitution went in here for I single, and that's this. Except there's one more tricky bit that this thing's got for us, is that what we've ended up substituting in is something that we already substituted in and something that's not fair to leave in the final expression. I have another I single here. And I already said we can't leave I singles because it's not something that we supply. It's not something we can govern or really look at or watch. And we don't know how fast it's being supplied because the reaction supplies it and we don't supply it. So what I'm going to do is substitute in for I single again. Well, what's the value of I single? Well, I set it back here. This is the value of I single. So I'm going to take this, I'm going to put it in for this I single, and that's how I get two of these multiplied together. And of course, when you multiply square root of something times itself, it unzips the square root, and this just becomes K, K1, and molarity of I2. The H2 remains because it isn't squared or anything, and also it's one of our original reactants. So now we have an expression for the rate law that involves only chemicals that we know, because the H2 remains and the I2 popped out of its roots, square root here because we squared it. And then the last thing here is that people say, well, you missed the K. The K's disappeared. You're just throwing away K's. But K is a constant number. I don't know what it is, but it's a very certain number, and the square root of it is a very certain number. And so it doesn't even matter if you realize that it's squared. The square root of K is a certain number, and the square root of this K is a certain number, and that K is a certain number. And I don't know what they are, but if I did, I would know for absolute certain what their product was. It's not in question, really. All I have to do is go look them up. I mean, if I could go look them up. If I did know the value of K1 and K2, I'd know what, and then this is multiplied, both of those are multiplied by this K, remember? Actually, you know what, they kind of forgot that. Here's the K from back here. But all three of these numbers are very certain numbers, and when you multiply them, you get another very certain number. And I'm not sure what it is, but it is not in, it's not a variable. It's a very certain number. So here's my sort of K4 or K overall. There is no step 4. I don't mean that there's a step 4. I mean the K overall. And we've reduced this down, and now we have a rate expression that works for reactants that are actually in the overall reaction. And does it match the rate law that we experimentally determined before and we're very confident of? It does. So do these steps seem to create a rate law that we were confident of? Yes. Those steps are almost certainly the way that this reaction happens, because when you do all this little bit of complicated substitution and so forth, you get a rate law that actually matches reality.